So we'll take furthermore two more problems in the index properties of soil, which are very, very important. So out of this two problem, one is the sand replacement problem, in which how to find it out the unit weight, in situ unit weight of the soil, and one of the problem is related to the shrinkage limit test. So these are the two problems related to the field or lab test. So sand replacement is particularly a field test which is used for the determination of the in situ unit weight of the soil, and the statement, and these are the given data. So first, the given data is weight of the excavated soil. So in order to determine the unit weight of the soil in situ unit weight, so we must have the weight of the soil divided by the volume of the soil. So weight of the soil, which is directly given it in the first term, which is 761.25 grams. So this is weight of the soil, 761.25 gram divided by volume of a soil. And we have also discussed, in order to determine volume of a soil, we use the sand replacement technique, sand replacement method. So as stated earlier, we have the hole, will form a hole inside the ground, and you'll fill this hole with sand. This is dry sand, we'll fill it with the dry sand. So initial weight of the sand in the cylinder, initial weight, so which is W1, is given. Initial weight of sand and the cylinder, which flap is there here, initial weight is given it as 10,500 gram. This is the initial weight given. So once you pour this into the hole, as also discussed earlier, the sand will form a cone, or will form a heave like this, and this angle particularly I referred it as a theta, which is the angle of repose of a soil, right? Angle of repose of a soil. So this is the cone weight. So the total weight which is gone inside the hole, which is nothing but, so total weight I'll write, total weight, which includes the weight in hole plus weight in cone, which is nothing but the difference in between the weight level between initial and final. So initially you have 10,500, and then after pouring the weight has reduced to 9,450 gram, and this becomes equals to 10,500 minus 9,450, it gives 1,050 gram, which is a total weight in the hole as well as in the cone. And now if you just pour it for the cone, then the weight has gone again reduced from 9,450 to 9,005. So therefore cone weight, I'll write it over here, so cone weight will be 9,450 minus 9,005. It becomes 945. 450 minus 9,005. No, it becomes equal to 445. Become 445 gram. So this is only hole, only cone. Sorry, not hole. It is only cone weight. So the weight of the sand in the hole will be this total weight minus cone weight. Therefore, the weight of sand in hole will be 1,005 minus 445 grams. So it becomes 560 grams. So this is the weight of a sand in the hole. True weight. This is the true weight. weight of sand in hole, only in the hole. This particular type of cone has been deducted from this particular total weight, so it gives you this weight. But again, in order to find it out, the density of a sand, the weight of the sand in calibrating pan is given as 1500 gram, and volume of this calibrating pan is given it as 1000 cc. So therefore the density of the sand equals to 1500 gram divided by 1000, which gives equal to 1.5 gram per cc. So therefore the volume of a hole equals to weight of sand in hole divided by the just the density of a sand, which becomes equal to 560 divided by 1.5. So this volume become equal to 373.33 cc, that is cubic centimeter. So therefore gamma in situ, that is bulk unit weight of the soil in field, is equals to the weight of soil, which is 761.25 divided by volume of a soil, which is 761.25 divided by 373.33, which it has 2.039 gram per cc. So this finishes the sand replacement problem. So in the same problem, what we have discussed is how to evaluate the in situ weight. So you just need to find it out the unit weight of the sand, or so unit weight of in situ unit weight of a soil by indirectly measuring its volume with the sand replacement method. So here it is. So volume of a soil is indirectly measured by the sand. So you just need to do some of the calculation and you will get the same answer. So that's all about the problem. So next problem is based on the shrinkage limit test. So the problem statement is like this. We've got the initial weight of the saturated soil as 30.8 gram, and the same volume at the same water content or same condition of the soil is 18 cc, that is 18 cubic centimeter. Once you dry the soil in an oven, the weight of sample got reduced to 20.5 gram, and corresponding dry volume of a soil is 12.5 cc. So in the same problem, the shrinkage limit is asked, shrinkage ratio is asked, and the specific gravity of solid is asked. So I'll begin solving this problem by just conventional three-phase diagram. So we have a total weight, or I'll call it as a saturated weight, initially given it as 30.8 gram. So once you oven dry it, the total volume was decreased, and also the water content has got decreased. So once you dry it in the oven, that's how you will get it. We have only solid and air. This much is the solid, and this much is the air. So initial weight is given it as 30.8 grams. Overall weight 30.8 gram, and initial volume given it as 18 cc, 18 cubic centimeter, right? So final weight of solid is given it as a 20.5 gram, and therefore this weight and this weight has to be same, so it became 20.5 grams. So initially water which is present is 30.8 minus 20.5. So initially water weight which was present is 10.3 gram. So this is 10.3 gram, that is weight of the water which is initially present. This is the initial weight, 30.8. So therefore this is after oven drying. The total volume at this case was found to be equal to 12.5 cc. And you have remembered from the classical definition is that if you plot water content versus volume, you have got this particular volume as a dry volume, and at shrinkage limit as well the volume is equal to dry volume. So therefore at shrinkage all the voids are filled by the water. That's the only difference. This is at shrinkage limit, and still at the shrinkage limit the degree of saturation is 100%. That means all the voids are filled by the water. So this is the solids and this is the water, except everything except the degree of saturation and air, we have all the voids filled by the water. So that's how the difference. So at this shrinkage limit, and we have particularly this is before oven drying or at natural case, the volume which is something around 18 cc and had got reduced up to 12.5 cc. So this is at shrinkage limit, right? Therefore you just asked to calculate this weight of water to the weight of soil. Weight of soil solid is known to us, which is 12.5 grams. And initially as well you have given every data related to its water content and all. So in order to determine the shrinkage limit, first of all we have calculated the weight of water which is initially present. From the weight of water I can calculate the volume of water which is initially present. Therefore the volume of water which is present, since the unit density or mass density of water is 1 gram per cc, and everything unit is in between the weights in grams and volumes in cc. So therefore the volume of water initially present is nothing but same, 10.3 cc. So that's how you will get it, the volume. And if you just notice, the total volume initially is given it as 18 cc. So if you just deduct this volume of water, you will get the volume of soil solid, right? So therefore this volume will be equal to, I'll write it over here, 18 cc minus 10.3 cc. So which is nothing but 18 minus 10.3, 7.7 cc. So this is solid volume, and therefore weight of solid divided by volume of solid, you will get the density of soil solid, which is nothing but 20.5 divided by 7.7, which is nothing but 20.5 divided by 7.7 is equals to 2.66. You will get it as 2.66 gram per cc. Absolutely, gram per cc. So I'll continue on the next page. Same problem. We have evaluated the density of soil solid, which is 2.66 gram per cc. So G of solid, which is nothing but a specific gravity of soil solid, is nothing but the ratio of the density or mass density of soil solid to the density of water. So therefore here GS will become equal to 2.66 divided by 1, so it is 2.66. So let's also calculated G value, which is 2.66 from this expression. So again I go back into the three-phase diagram, and I'll write, since we have calculated this particular volume as 7.7 cc, this will remain same. So at shrinkage limit also this will remain same. It has 7.7 cc because solids are relatively incompressible, therefore will not be any change in weight and volume of the soil solid. So at the shrinkage limit also we have total volume equal to 12.5 cc. So therefore volume of the water present here will become equal to 12.5 minus 7.7, which is equal to 4.8 cc. So similarly, the same way, even if you multiply by unit density or mass density of water, you will end up at the same answer, that is weight of the water at a shrinkage limit equals to the 4.8 cc. So weight of the water at shrinkage limit is equals to same way 4.8 gram. So therefore shrinkage limit is nothing but the weight of water at shrinkage limit divided by weight of dry soil or weight of soil solid only, which it becomes 4.8 divided by 20.5, answer into 100 expressed in percentage. The shrinkage limit will be 23.415 percentage. This is the shrinkage limit. You have calculated G, you have calculated shrinkage limit. Only one thing is remaining, is the shrinkage ratio. So from the classical definition of shrinkage ratio, which is nothing but the slope of this particular type of curve, is volume versus water content, slope of this curve S divided by Vd is nothing but classical definition of shrinkage ratio is. So V1 minus Vd divided by W1 minus Wd whole thing, this is the slope divided by Vd into 100. So that's how is the definition of shrinkage ratio is. But we have also again seen the shrinkage ratio definition by replacing this water content in terms of volume, and we end up at this particular expression, if you remember, gamma d by gamma w into 100%. So even if you not 100%, it's none of the case. So shrinkage ratio is just the ratio, so not you should multiply by 100, that's what it means. So it's gamma d and gamma w, and in that lecture we have seen gamma d, you need to take the dry unit weight at shrinkage limit. That's what I have highlighted in your previous discussion as well. So therefore, because if you have assuming if you just take this particular volume, then your answer will be wrong. So therefore you need to take a dry unit weight at shrinkage limit. So dry unit weight means this divided by total volume, which is nothing but the 20.5 divided by 12.5 divided by gamma w is rho w is 1 gram per cc. So you'll end up at evaluating 1.64. So summary, we have calculated GS 2.66, we have calculated shrinkage limit WS as 23%, and we have calculated also shrinkage ratio, which is nothing but 1.64. So this is the summary of the problem, and hopefully you got the same problem and might be asked in the future. So this finishes all the problems in the index properties of soil. uh, Thank you.